So yeah, let us continue. Today we will finish the layered intrusion class, and then we have only 2 weeks left. So now we discussed the different cumulus minerals. We discovered that layering can only be formed in silica undersaturated rocks because of the network forming and the network modifying cations. And we discussed how a primitive metal melt looks like. And we discussed, or I told you, where we can find the most common or the most important layered intrusions. So it is all written here in chapter number 4. So I showed you also some pictures from layered intrusions and about the dihedral angle, that if the dihedral angle is smaller than 60 degrees, then we can have an interconnected network of volatiles or fluids. So, and then we can enrich somewhere some elements. So, but I told you also that layering is by now not completely understood. So, and I told you what different kind of layering we can find. That was the cryptal layering, the modal layering, and so on. So that is all written there, and you have all the pictures. And in the exam I have there also some questions. So now we know about, or a little bit more about the layering itself. So, but now we have to go for our ore deposits, yeah? So, and I told you at the beginning when we talked about the general things, that certain elements become enriched in the magmatic stage at very high temperatures. So, in one mineral, that is the chromite. So, in the chromite will crystallize very early in the crystallization sequence, you know this by now, and due to the high density, the chromite will then sink down to the bottom of the magma chamber. Yeah? So, and there you are forming large horizons of chromite. So, and the biggest chromite ore deposit, that is, you can find this in the layered intrusion at the Bushveld complex in South Africa, and there you have huge chromite layers of 1 to 1.5 meters thickness. So, and they can just mining them with a digger, yeah? So, and that is number 1, that is the mechanism of ore enrichment during the magmatic phase. And here we have, for example, the chromite. So then number 2, we have the unmixing of non-mixable melts. Maybe we can make it here a little bit bigger, because you are sitting always in the back, because you are afraid of me. So, home. Zoom, let us go to 100. Is it then? No, then it is too small. Enter full screen. No, that is also not that what we like. Ah, yes, 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 that's great, thank you. So now it's bigger. So then another thing, the unmixing of two non-mixable melts. So and therefore we have actually the sulfides. And those of you who are doing also the ES303 with me, then you have heard this just a few weeks ago. Yeah? So a sulfide ore deposit is always formed if we have two unmixable melts. So and therefore you get the sulfide drops. Yes. Late unmixing will form only dispersed sulfate drops. So and then we have the late crystallization of some other minerals, for example the magnetite and the ilmenite. Yeah? The ilmenite is very important for titanium and the magnetite is very important for iron. Yeah? So and this is then very interesting if you are looking for elements like vanadium. Yeah? Vanadium, that is one of these very expensive metal, and they are forming after the chromite. Yeah? So the chromite, we have the early crystallization, and the vanadium-bearing minerals, also these platinum group elements, yeah, they are forming in this stage as well as the titanium. So and they are becoming enriched during fractionation. So and you know by now also what fractionation is. Yeah? You are removing always elements from your melt and therefore you are changing the chemical composition permanently from your residual melt, and there you can then enrich some elements like the vanadium. So but that is still at very high temperatures in the magmatic stage. Don't mix this up with the hydrothermal stage. These are two pairs of shoes, yeah? So, and these are the three things how you can create ore deposits in a layered intrusion. So then we have here the next thing, differentiation of a melt. So we have primitive basaltic magmas, and I told you such a primitive melt has the whole rock has an X and G of 0.68 and is in equilibrium with an olivine with an X and G of 0.9 and 3000 ppm nickel. So, and what is written here, primitive basaltic magmas changing, of course, during crystallization, their composition. So, at the beginning, you are enriching then your chromium. Later on, I mean the chromium, you are not enriching the chromium, it becomes formed, and the mineral who contains the chromium is the mineral chromite, and this chromite becomes then removed from the melt and sinking it to the bottom, yeah? So, and then you have already changed the chemical composition of your parental melt because the chromite is removed. And later on, during differentiation and fractionation, you will then change always the chemical composition of your melt, and different ore minerals will become formed. So then we have a basaltic melt, and from this basaltic melt, olivine crystallizes then, and then it is more pure in silica than the basalt. So, but if we are crystallizing the olivine from our melt, then we are removing always more and more magnesium. So, and if you are now switching again to our ES303, what is written here, exactly this, what you have done in your CIPW calculation. If you are starting to crystallize in this melt, then apatite, then this melt becomes depleted in phosphor. Yeah? So that's always the same game. So in those elements which cannot fit in any crystal lattice, they are becoming then enriched in the residual melt. So and there I have every year a question in the examination, and you can be sure that it is this year also inside, and there I would like to know these fractionation laws about compatible elements and the incompatible elements. And I gave for this, or I give for this 8 points out of 146. So, and those mineral elements which can be fit in easily in the crystal lattice, these are called the compatible elements. Yeah, you know this by now as well. So, if I like to enrich in the layered intrusion, for example, uranium. So, and a lot of this layered intrusion, there you can find uranium here in minerals. Like in this layered intrusion in South Greenland, where I did my master. Therefore, my hand is still always a little bit shiny because of all this radioactivity there. So, and when do you think, I mean, a uranium, is this a compatible element or an incompatible element? It's an incompatible element, yeah? Uranium is very big, yeah? So and then it cannot fit easily in the crystal lattice because it's a big bubble. So and then uranium has a lot of electrons around, yeah? So even the whole cloud is very big. So and therefore uranium becomes then enriched in the residual melt and will become formed later. So those incompatible elements, for the incompatible elements will form ore deposits which will be formed in the later stage and therefore at lower temperatures. Yeah? So but if we are now looking for the chromium is very compatible, but chromium crystallizes then very early, so that will be formed at higher temperatures, yeah, or very high temperatures. So but if you are looking then for nickel. Nickel is an extremely compatible element, and the nickel atom, where does the nickel atom go? That you must know by now. Which mineral will take up the nickel? So which mineral will be formed very early at high temperatures? It crystallizes actually before the chromite crystallizes. That is the mineral olivine. So because the metal olivine can have 3000 ppm nickel. So and these elements becoming then very early removed from the crystallization sequence from our crystallizing melt and will fit in minerals like the chromite and the olivine. Yeah? You must only read the text, then you can answer the questions. So when you are looking at these elements in these minerals, I mean you can make analysis on them with an electron microprobe, and these are then an indicator how strong a melt or a magma became fractionated. So, and if we are looking for potassium, potassium is a very incompatible element. So, and there it becomes enriched in the residual melt, and especially then when the melt becomes then felsic. Yeah? And there the potassium, in which mineral will you find the potassium there? That is in the K-feldspar. So, and therefore, we are forming then a granitic melt. So, and generally one can then say that the chromium ore deposit is only formed there where you have a very primitive melt. And the very primitive melt is the original melt. So a primitive melt, if you are switching now to ES303, a primitive melt is then where, in which geotectonic setting you are getting the most primitive melt on Earth. I mean, we discussed there the warp, the oil, the CFB, the continental rim, and all these things. And where do you get the most primitive melt? That is at the Middle Ocean Ridge. So, and the crystallization of a primitive basalt can be described using the forsterite, anodite, and diopside triangle. I will show you then the triangle. So, and that means the plagioclase becomes then unstable when you have very low chromium levels in the melt. So varying between 100 and 1000 ppm chromium. So, and that means that the primitive basalt has to crystallize the chromium before, at low chromium concentration, the melt in this melt feldspar will become stable. So, and there is a mistake, that is here not unstable, that is stable. So I will then just upload the correct version. So then you can have, whether in your basaltic melt, you can have a plagioclase or a chromite. Yeah? But of course you can have some chromites inside as small relicts. So, but you will not have in your very solid and very thick chromite layer, you will not find only one plagioclase. Because the plagioclase was formed later when all the chromite was already removed, and then you have only small concentration of chromium in the melt, but with this small concentration of chromium, you cannot form a chromite. Yeah, just let us continue with the text and I will show you afterwards these triangles. So now we have, or we will talk, or I will tell you something about the mechanisms for the formation of these layers. So, and there are a number of processes which leads to the formation of these different layers, which you can observe in the layered intrusion. So, and all this process together will then play a role in the formation of such a layered intrusion. So that means there is no universal or no general mechanism to form this layering. So in the complete process for the formation or of the formation of layered intrusion is by now not very well understood. So some mechanism they are playing a role while the magma entered in the magma chamber. Whatever a magma chamber is, that is by now also not clear because there are no holes in the Earth's mantle where magma can enter. That is all a process of assimilation, contamination with the surrounding areas. So some of them, at the beginning of the crystallization, they are dominated by a silica-rich melt, and then you are producing a crystal mesh. And of course, if you are starting with a silica-rich melt, then you will go down with the silica concentration, and therefore, when you are going down with the silica concentration, then your melt will become more and more mafic, and therefore you have a change in the viscosity. We discussed this also before, and therefore you will form these layers. So, at first you need your crystal mesh, and then you need subsolidus cooling. So you know by now what the liquidus is, and you know by now what the solidus is. If you are going down to the solidus and touching the curve of the solidus, then you will form first minerals. And by the formation or during the formation of the first minerals, you will then produce this crystal mesh. So, and if your different minerals are then connected to each other, then the viscosity of your melt becomes lower, and therefore you can then form these boundaries. Yeah, and in all this layered intrusion, you have a boundary. I mean, these are always boundaries, and then you have your different layers. So in there you have to form a boundary of a small rigid crust where no exchange with the surrounding melt is possible. So then we have here the different processes which can cause layering. So we have mechanical separation. So, and that is while your magma is entering the chamber, all of your crystals in the melt are in suspension, yeah? So they are smearing just wild in this melt around. The percentage of crystals can be up to 50%. So, but then, if your melt has more than 50% crystals, or your magma has more than 50% of crystals in the melt, then what happens then? Then your melt is not longer eruptive and it is not longer flexible, because then the network between all your minerals are becoming more and more connected, and your melt becomes then more and more low viscous. So, and therefore, large crystals with a higher density, they will sink faster. So, and these large crystals with the higher density, they are becoming then connected to each other, and therefore you are forming then a solidification front. So, and I told you last week what a solidification front is. So, you need always a solidification front in your or to produce layering. So then number 2, we have magma mixing, and this magma mixing is then responsible to form, for example, rich monomineralic layers, and the monomineralic layer in such a layered intrusion, these are the chromite, or the chromite horizon. So, and that is important, that is just when a primitive melt enters the chamber and then it becomes fractionated and your chromite becomes then separated because it is sinking to the bottom of the chamber. So then we have a change in oxygen fugacity, then the change in pressure. For example, when the magma is entering the magma chamber, and also where it is, from where it is arriving, yeah? So because when your melt is maybe produced here at the crust mantle boundary and it's rising up, then you have a release in pressure. So then we have late magmatic processes, and these late magmatic processes are causing then also a change in the chemical potential or in the gradient. So and that leads to the transport of material, and it can then form polymineralic layers. So and for example, this layered intrusion where I did my master thesis, there we do not have such chromite layers and so on, but we have their polymineralic layers. So in these polymineralic layers, that is just a transport mechanism of different materials. So now here are some diagrams how the chemistry changes with the depth. So here we have a depth, I mean they made just drill cores. Here we have the depth. So and the total depth is here 100 meters. Here we have 460 meters. Here we have 70 meters. So in the area they have them discovered, or probably they made drill cores, and then they have taken samples from different depths. So and here we have then the distribution of mafic minerals. So and it depends strongly on the depth how the distribution of your mafic minerals are. Yeah. So at here we have the much more olivine. Yeah. So because olivine makes this stuff mafic. Yeah. So if you have that much olivine inside and you are looking for a chromite ore deposit, in which depth you would then look like? The chromite is crystallizing out together with the olivine, and then you are expecting here the most ones, yeah? So here you are expecting the lowest concentration, yeah? So then we have here a total depth of 460 meters. So at 460 meters, so and there they have the density. So and for doing these density plots, you do not need a drill core, you can just calculate this. Or even I can calculate it. Yeah. So and if you have here the density, where do you expect then the highest chromium and titanium concentration? Here we have the depth of total 460 meters. Here we have high density. Here we have low density. So where do you expect then the chromite and the ilmenite, the magnetite? So does the chromite have a high density or a low density? No, it's high density. So because otherwise the chromite will not crystallize very early in the crystallization sequence and it will sinking down to the bottom of the magma chamber. Yeah? So and here we have the XMGO or MGO concentration in weight. So and if you are checking here that is from Hawaii, so and where do you expecting then the highest chromium and titanium concentration? Or where do you expect the highest nickel concentration? So which nickel is a compatible element and in which mineral or in which crystal lattice of which mineral nickel becomes built in? In the olivine, yeah. So does the olivine has high magnesium, does the olivine cause high magnesium values or low? Such a mantle olivine, I mean, does it cause then high magnesium values or low? High, yes, you said it, yeah? Is it? No, I have here some prizes. So, and I'm always waiting that I can get rid of this stuff here, because I'm having this always in New World. Yeah, you can put in your beer can and during summertime it is then or it will be remain cold, and during winter time it becomes warmed up. So that is just from South Pacific brewery from Papua New Guinea. I have still a lot left in my plan, yeah? But you have to answer the answers correctly. So, yeah, exactly one is left. And that's for me now. So that is, these are some assumptions or some calculation how they are doing it. And here you have then, if you have here high magnesium values, then this stuff here is formed very early at high temperatures, yeah? If you have not the influx from a second melt. So what do we have here? We have the size, the percentage, and the mode. So here in this diagram you have the mode, the percentage of olivine, autopyroxene, and plagioclase. So at the beginning you have a very low concentration here in this example in the height of the layer, that is again the height. You have very low concentration of olivine and very high concentration of plagioclase. So that means the olivine was, or a lot of olivine was removed from the melt. Yeah? because it's just sinking to the bottom of the chamber, yeah? So, and if you are going here, I don't know if this is now the bottom of the chamber, but then it's at least the height of the layer. So, and here we have this at the bottom of the layer, yeah? At the bottom of the layer, we have nearly 50% of olivine, yeah? So, and we have about only 30% of plagioclase here. So, in the pyroxene, that is then 20%. So, and here you have a crossing point. So, if you are looking here at the top, we have then very high concentration of plagioclase, yeah? So, and of course, if you are looking then for these very expensive metals, then you are looking somewhere here, yeah? Because these very expensive metals, they are not associated with a lot of plagioclase, yeah? So if you are looking for strontium minerals, barium-bearing minerals or something like this, then you are looking here. So then we have the distribution of the grain size. So what tells us this? Here we have the distribution of the grain size of the olivine. You have much lower concentration of olivine, but the grain size here is bigger. So what means this? That means that these olivine crystals here has cooled down much faster compared to those ones here, yeah? So because if a mineral is bigger, then the melt is cooling down slower. If the mineral is smaller, then the melt cools down faster. And if you have a glass like this obsidian, then your melt will cool down very fast. So, and here we have just different models about the grain size, distribution. For example, in A we had the mode, in B we have SWOS, that is the theoretical grain size distribution through the layer in A. Yeah, that belongs then to this one. So, and here number C, that is a theoretical distribution in which grain size for all phases increased downwards. In this model, or in this theoretical model, we have downwards lower cooling rates and upwards faster cooling rates. And in number D, that is also a theoretical distribution in which grain size is positively correlated. So, but that is now for you as an ES301 student not that important. Important is for you how the chemistry inflects the different layers, and that you have slow cooling processes, then you are forming bigger crystals. You have fast cooling processes, then your minerals are smaller. So then we have different models of magma chambers. And that you should also watch very carefully, because it can be that I will have a question of this in your exam. So we have here just a classical magma chamber where it cools from outside to inside. Yeah, that is the classical magma chamber. Here we have the olivine, here we have the diopside, here we have the silica. So, and you are cooling them down from here to here, yeah? Here you have, it cools down very fast at high temperatures. So, and therefore you will form here minerals at first like olivine, yeah? So, in this classical magma chamber, that is just the textbook, yeah? Because you will not find, I think, in nature such a classical magma chamber, because there are a lot of different mechanical and chemical processes involved. So later on at lower temperatures, you will then form here a CPX. So in the very low temperatures, you are going down, your silica concentration becomes higher and higher, and you will form in your residual melt. You can fractionate it down till you are getting a granite. You know this by now. So in there you will then get different ore minerals in different zones of your magma chambers. So then we have here forming in this magma chamber, we are forming now a solidification front. And the solidification front, that is then the case when you are forming layering. Without a solidification front, you cannot form any layering. That is important. So and there you are starting then also here with your fractionation processes or with the process of a solidification front. So in this solidification front, there is then a network, and this network forms then a boundary, and that is important for the layering. So and there you are forming also at first minerals which can be formed at higher temperatures, and at the end it becomes then here, or we have here this situation, we have here a silica rich melt, and there you have then your more mafic minerals, and these mafic minerals are those minerals which makes your layered intrusion. So and then we have the solidification front as well here. Here you have your solidification front, but here with phenocrystals. So in the phenocrystals, these are these minerals which crystallizing very early out into a crystallizing melt, like the chromite. Yeah? So and this chromite is then sinking here to the bottom of the chamber. So and here we have the chromite at the bottom of the chamber, or actually you have more chromite at the bottom of the chamber because due to Stokes' law, that means the differentiation processes, the chromite will sink here to the bottom, but of course you are cooling it down very fast here from outside everywhere from your country rocks, and then you will have there also some minerals which will be formed at high temperatures. So what is for you important? Solidification from causes then magmatic layering, no solidification from no magmatic layering. This we don't need. This we need. Something similar you got also in ES301. Here we have the cooling rate, yeah? The cooling rate in temperature. And the delta is here just the difference in temperature. And then we have here the crystallization rate. That means the size of your minerals. So and if you are going here down at 0.1, then you will form very fine grained accumulates or accumulus minerals. So if you are going back to the class from last week, then I explained to you what accumulus is. Yeah? So these are then very fine grained rocks. So at number 2, we are just going there. Then we are forming then the autocumulates. So in the autocumulates are showing crystals which are bigger, but they have more interstitial material inside, yeah? Because the accumulates, I told you this last week, has less than 5% interstitial material inside, and interstitial material that is just the residual melt, yeah? So whereas autocumulates has much more interstitial material inside. And there, number 3, we have very coarse-grained autocumulates. And such coarse-grained autocumulates, these are the huge minerals, this can then be, or there you can then form pegmatites. So in such layered intrusions, I showed you this last week, from the example from Greenland, there you have also a lot of pegmatites, and these pegmatite veins, I saw it by myself in nature, they can be of this size, yeah, they are really huge veins. So if we are going to number 4, then we have volcanic textures. So and if we are going here to number 5, then we have glass, and this glass that is actually our obsidiate. So because here we have a high cooling rate, we are cooling very, very fast, yeah? Here we have a low cooling rate, yeah? So we are starting here to cool, and here we have a low cooling rate. We are forming bigger crystals. If we have a high cooling rate, then we are forming glass. So here we have another triangle, and we are using in petrology always these triangles because we can show complicated or complex things very easily. So here we have a gabbro, and this gabbro consists of silicates, and you know what a gabbro is, that is an intermediate rock, and you saw the gabbros here from Fiji, you saw it during the ES301 field trip in the Yamuna Creek. Yeah? There you saw the gabbros and you saw the dolomite. So, and here we have the starting composition of our gabbro. Yeah? We have a magma or this a gabbroid melt. Yeah, a gabbroid melt. So, and this magma consists then to 99% of silicates. Then we have 0.3% of sulfite and 0.7% of oxide. On this corner we have the oxides, on this corner we have the sulfites. So if we are following this arrow here, then we will crystallize from our magma, from our gabbroid magma, we will crystallize autopyroxene and plagioclase. Yeah? So that means we are removing all the magnesium, the iron, the silica, we are removing everything. So and therefore we are removing all these minerals from the melt, then the silicates in our magma becomes then always lower, the silica concentration, because we are removing them, yeah? So and therefore we are going down to this curve, and then we will produce, or we will enrich in our melt all the sulfides and all the other oxides like magnetite, yeah? We will remove them from our melt. No, these ones we will enrich in our melt due to the fact that we are removing this stuff. So, and therefore you can then make a sulfide or an oxide deposit. So if you are by some geotectonic movement, or not a movement, if you are cooling your melt here very fast down, yeah, so that it becomes frozen, then if you have this composition, you must not even think about to mine some sulfides or oxides there, because it has not become enriched, yeah. So you have to wait till everything else is removed, and then you are enriching or forming layers or something like this, where you can then mine this oxide and the sulfides. That is what this diagram is telling us. So the next one tells us something similar. We are just going down along these curves. So if we have a composition like here, then we are going down to this curve, and then we will crystallize, let us say, 70% sulfides and 30% oxides. If we are going from this point to this point, then the distribution of sulfide and oxide will be different. So here the same, I mean we have here our silicates, here we have a two liquid field, so here we have sulfide liquidus plus a silica liquidus, and here we have the same for the oxides. So along this curve we will then form spinel plus liquid, and on this form we will form sulfides plus liquids. So and here between we have our silicates. Here the same again, that is now not that important. So, but this one. That is, for example, the interaction between a silica, olivine and chromite. Here at the top we have silica, here at the corner we have olivine, here at the corner we have chromite. So if we are going down this cooling path, then you can see how many % of chromite you will crystallize and how many % of olivine you will crystallize. So it is just when your melt becomes cooled down. So and that is a temperature depending thing, and you know this by now as well. If a melt cools down, then you will form bigger crystals. And here there is this relationship between chromite and olivine. So, but the thing is, we are not going down here with the cooling curve, we are going up here. That's the way, because here are the arrows. So now we are done with the layered intrusions, and then it's only the geophysics left and the geothermal. So any questions? I will hand out then in 2 weeks test number 2. So and then you should study both tests, and if you have studied both tests, then you should be able to pass the examination. That is for ES301 as for ES303. So for the continuous assessment, I will mainly mark, or actually I will use the 2 tests. So your exercises, I will use them if somebody is then on the boundary. on the boundary means if somebody has maybe 45% or in the exam together with the two tests, then I need something to lift you over. Yeah, otherwise we are done for today. Yeah? Because next week with the geophysics I can do easily next Friday, and the geothermal I can do easily on the following Friday.